All right, so in this case, y equals 3. So let's see what that looks like. Here's 1, 2, 3. This is my graph, right? Y equals 3. Okay, as I'm approaching x equals 2, what y value is the graph approaching? 3, right? As I'm approaching y equals 5, what value is the graph approaching? 3. So the limit of that is just 3. Now, what if I'm looking for the limit as x approaches c of x? So this time, the graph is y equals x. And that looks like this, right? So if on the x-axis I'm approaching, let's say 3, what y value is the graph approaching? 3. If I'm approaching 5, what y value is the graph approaching? 5. So here, right, the function, the limit is going to be the function at x equals c. So the limit of x as x approaches 3 will just be 3. Okay, now, here are some properties for us. So L, M, C, and K are real numbers. The limit of f of x as x approaches c is L. The limit of g of x is M. Okay? Now, if I want to find the limit of f of x plus g of x, right? I find the limit of f of x separately, g of x separately, and I add them. So it's L plus M. Subtraction is the same. Multiplication, division, all the same. All right? Let's do a couple. All right, so what about this one? The properties of limits to evaluate the following. The limit of 3 as x approaches 2. What do you guys think? Limit of 3 as x approaches 2.
Would be 3.
3. Okay, now take a look at this one. The limit of e as x approaches radical 2. So the function here is y equals e. Okay? What is the limit of that as x approaches root 2? Huh? It's just e. Because you know what? What does y equals e look like? Well, here is 1, here is 2, here is 3. This is 2.7. That's what y equals e looks like. So it's just e. Okay? Same thing with, if I said, for example, the limit as x approaches to pi of e. Still e, right? Okay. Now, here we're going to use the properties to evaluate this, and I'm going to do it once. So everything, right, all the limits and stuff, we always compare it to our basic identity functions and the constant function. So we're going to use these two properties to evaluate the rest of those. So here's what we're going to do.
Are we going to be given a list of properties?
No, you need to know, because look at how easy it is. So this is the limit as x approaches 4 of 6x squared minus the limit as x approaches 4 of 6x plus the limit as x approaches 4 of 3. All right, now I know what the limit as x approaches c of x is. So let me write this in terms of that. This is 6 times the limit as x approaches 4 of x squared. Okay? So you see how I separated the 6x squared? Minus 6 times the limit as x approaches 4 of x plus the limit as x approaches 4 of 3. The reason why I did that is because I know what the limit as x approaches c of a constant is, and I know the limit as x approaches c of x, right? So, how much is just this, the limit as x approaches 4 of x? Just this. How much is that? Limit x approaches 4 of x. This is x. What's the limit as x approaches 4? 4. So then this is 6 times 4 squared minus 6 times, that's also 4, plus how much is the one on the end? just 3. Okay? So now, this is going to be, take out your calculators, figure this out for me. 6 times 24, I'm sorry, 6 times 16 minus 24 plus 3.
So can we just simply plug that in?
You actually could.
Wait, it's 2 times? Or 6 times 16, right?
Oh, 6 times 16, I'm sorry. Yeah. All right, so take a look then. Let's summarize this, okay? I always do this one time, and I want you guys to figure out what the shortcut is. And the shortcut is, if you're dealing with a polynomial function, right? If p of x is a polynomial function, then the limit as x approaches c is just p of c. What does that mean? All you have to do is use direct substitution. You don't have to do all this. You could just do it directly by substitution. Okay? All right. Rational functions, same situation. Direct substitution because you have a polynomial here and a polynomial there. Okay? All right. So now here's what we're going to do. And, okay, I need you guys to be quick with me. Here, we're going to use direct substitution. So the limit as x approaches 2 of this, right? So I just simply plug it in. 2 minus 3. 2 times 4 minus 2 minus 15. That's negative 1 over how much is that on the bottom? How much?
Yeah.
9. So this is going to be simply 1 over 9. Okay? All right, we're going to do the same thing here. We're going to plug negative 1 in there. So what'll that be? Root 2. And that's all. The limit is just root 2. Okay? What about here? DNE. Okay, so why is it DNE? Right? Why is it DNE? What does that look like? That function. What does that look like? That's a square root, so what does it look like? Right? Right? Okay, but where does it start? At 0?
No, it's 6.
At negative 6, you mean? At negative 6. So here's how that function looks. Where am I asked to evaluate it? At negative 8. There is not even a function there. That's like barren country, right? So it's DNE. It doesn't even exist there. Okay, what about this one? The limit as x approaches a, right? We just plug in a in there. Okay? Now, this is all the not so exciting stuff. So let's get into some exciting stuff. Sometimes when you plug in your value for a direct substitution, we get 0 over 0, right? And 0 over 0, that's not 1. Everybody thinks it's 1 because you're dividing the same number by the same number. But remember, you can never divide by 0. And if it's 0 over 0, it's even worse. So in a sense, 1 divided by 0 is actually like yay better than 0 over 0. Like 0 over 0 is really bad. The reason why it's really bad is because when you get 0 over 0, that's really indeterminate form because you can't gather any information from that. 1 over 0 I know will be infinity. 0 over 0 I have no idea because if you get 0 over 0, it's impossible to determine the limit, okay? You can still, it's possible that the limit will exist or it'll be negative or positive infinity. So when you get 0 over 0, it's still possible that the limit exists, or you might just get negative or positive infinity. When you get 0 over 0, you have to use algebra to simplify your function. And here are some things you could do. One thing is factor, right? So here, when you plug in negative 2, what do you get on top when you plug in negative 2? Well, on the bottom, you get 0. And you know what? You get 0 on top as well. Okay? So 0 over 0, that's indeterminate. That means what I need to do is I need to factor this guy. So this is going to equal the limit as x equals negative 2 of bottom can't be factored, but the top, I have a cubic term with 4 terms. How do I factor that? Grouping. Yes, exactly what you said. All right, let's group them. So what can I factor out of here? X squared, and we get x minus 3 minus 4, x minus 3. Oh my, look at that. This is equal to the limit as x approaches negative 2 of x minus 3, x squared minus 4, x minus 2. Notice, when I'm doing algebra, when I haven't yet plugged in my value, each step, right, at each step I have to put in my limit notation. That needs to stay until the very end when I actually plug in a number. Otherwise, points off, AP test, points off, yeah.
Isn't that plus 2?
Yes. So this is the limit as x approaches to negative 2, x minus 3, x minus 2, x plus 2, over x plus 2. So now look at what happens. The x plus 2 is canceled. The reason why we got 0 over 0 is now gone away. At this point, okay, now I can plug in my 2 again, right? When I'm ready to plug my 2 back in, I can let go of the limit notation. So it'll be negative 5 times negative 4, 20. So you see that even though I got 0 over 0 in the beginning, the problem was not ready to be thrown away. I was still able to salvage it, right? Okay, let's do this next one. As you plug in x equals 6, you get 0 over 0. So here's one other notation. In order to save time, we put like 0 over 0 up here. Okay, so now this is the limit as x approaches 6. How do I factor that guy? X minus 6, x minus 1, and here 3x and x. Okay, so look. It's x approaches 6, right? Which is what's giving you a problem. So here you're going to get one of your terms to be x minus 6. Okay? And then does that work like that? So you could use that to factor. All right, that goes away. And now I can put in my 6. So it'll be 5 over 3 times 6 is 18, 25, 1 over 5. Okay? All right. We can also, okay, so another way we can get rid of that 0 over 0 problem is by rationalizing. Oh, it's back. Okay, and this is the reason why I want you guys to still rationalize in Algebra 2, because I don't want you to lose that skill. Okay, here, this is going to give us, when you plug in the 25, 25 minus 25, 0, 0, 0 over 0, not cool. So we need to rationalize. Multiply top and bottom by the conjugate. Yes. So now, this is the limit. As x approaches 25. Okay, what do we get on the bottom? The square of the first is x minus the square of the second is 25. Okay, now on top, here's what you get. X minus 25, root x plus 5. I know you have the urge to multiply that in using FOIL. Please don't, because take a look at what happens now. The entire term will cancel. So we get the square root of, so limit is x equal to 25, root 25, root x plus 5, this is 10, right? Yes or no? Okay. Now, what about here? What can I do there? If I put in a 0, I'm going to get, yeah, well, 0 over 0. It's indeterminate, not undefined. Right? I'm going to get 2 minus 2 over 0. Okay. Now I need to rationalize. So how am I going to rationalize this? What do I multiply? Not by x. You're gonna rationalize, meaning multiply by the root. You're gonna rationalize the root, the irrational part. So we multiply by 2 plus root x plus 4. 2 plus root x plus 4. Okay, in the numerator, I get the square of the first term minus the square of the second term over, don't multiply this in, this. Okay. Oh, I just lost points. What did I do? What did I not do? I forgot to put in limit. So this is the limit as x approaches 0 of, okay, can I do this in like in an intermediate step? If I distribute the negative, I'm going to get 4 minus x minus 4. What happens to the 4s? Go away. So I have negative x over x times 2 plus root x plus 4. What cancels? Just the x's. So this is the limit as x approaches 0 of negative 1 over 2 plus root x plus 4. So this is, now I plug in 0, negative 1 over 2 plus root 4, negative 1 over 4. Okay, having fun. So we talked about limits as x approaches a number. All right. What about limits at infinity? All right, what about limits at infinity? So the limit as x approaches infinity. Okay. Power functions. What are power functions? Power functions are y equals x to the n. Okay? And you can divide that into two categories. Y equals x to the odd number. Y equals x to an even number. If y equals x to the n, and n is even, right? If n is even, what does it look like? This is what it looks like. Both ends either face up or they face down. So, if it's a positive coefficient, as x approaches infinity, the function goes up. As x approaches negative infinity, it's infinity. And then if it's odd, right, one is a positive infinity, one is negative infinity. Now, we've mentioned this several times. If you have polynomial functions, right? So suppose you have y equals x to the 7 plus 2x to the 5 plus 3, right? If you look at the limit as x approaches infinity, suppose x is a really large number, like 1,000,000. What do you have here? 1,000,000 to the 5 and 1,000,000 to the 7. How many zeros in 1,000,000? 6. 1,000,000 to the 5, how many zeros? 30. Because, right? 30. 11 to the 7, how many zeros? 7 times 6, 42. Right? No. Sorry, I don't know what I said. Okay, 1,000,000 to the 7, right? 42 zeros. 1,000,000 to the 5, 30 zeros. So we're talking about like 1,000,000 times 1,000,000 more, right? So at infinity, these pale in comparison. They're negligible. So all we consider is this function over there. Okay? So using that knowledge now, take a look at this. Here I have a polynomial function, 4x to the 6, 3x to the 5, and so on. At x equals infinity, which of these terms is the only one that matters? 4x to the 6. And as x, okay, so that's an even function. Both will either end up or down. In this case, both are up. So as x approaches infinity, this is positive infinity. All right, so quickly do B, C, and D. I'll give you a minute. Okay, so what about B? How much? Positive infinity. What about C? And D? Negative infinity. Okay? Okay. All right, let's talk about reciprocal functions. Right? This is what a reciprocal function looks like. So f of x is equal to 1 over x. Can x ever be 0? No. Can y ever be 0? No. You can never divide by 1 by a number and get 0. Okay. Well, as x approaches infinity, what value does 1 over x approach? As x approaches infinity, what value? It approaches 0, right? You have 1 over x. If x gets infinitely large, 1 over an infinitely large number is 0. Okay. As x approaches negative infinity, where does f of x approach? What value? Negative infinity. Still 0. Okay, you just go to 0 from the bottom as opposed to from the top. Okay? So whether it's negative infinity or positive infinity, 1 over x will approach infinity. Okay. Let's talk about rational functions. What is a rational function? Rational function. Fractions. This is when you have f of x over g of x, right? Okay. So when you have x in the numerator and the denominator. All right, so we're going to compare the degree of the numerator and the denominator. Okay, this is an easy shortcut, but you know I don't like you guys memorizing things, so don't memorize this. If the degree of the numerator is less than the degree of the denominator, okay, then it goes to 0. Why? Let's take a look at this function. The degree of the numerator, you just take the highest term as x squared. The denominator, you take the highest term as x cubed. So this is going to be the limit as x approaches infinity, x squared over x cubed. This is going to be the limit as x approaches infinity of 1 over x. And if x gets infinitely large, 1 over x will equal 0. Okay, where do I want you to be with this? Do I want you to show all this work? Do I need you to show all this work? I don't. Where I want you to be is, you can look at this function at the very beginning, circle x squared, x cubed, and say, yep, that's 0. You have more x's on the bottom, all right? You're going to be left with an excess of x's on the bottom. As they get large, the whole thing gets 0. Make sense? Of course it does. It's math. Let's move on to the next case. What if the numerator has a degree equal to that of the denominator? Right? Like this one. The term with the highest exponent is that, negative 2x cubed and 6x cubed. When I put them, this is as x approaches negative infinity, when I put them on top of each other, the x cubes cancel, so I just have negative 1 over 3, right? So this will be just the ratio of the leading coefficient. Okay. If the numerator has a larger degree than the denominator, then it'll be positive or negative infinity or dne. So x to the 5 over negative x cubed. This is going to be the limit as x approaches infinity of negative x squared, negative infinity. Okay? All right. So I'll give you a minute, half a minute, to do A, B, and C here. Okay. The homework for this part is here. It's from the book, page 754. And it's those numbers. I've split it into two. So I want you guys to do the, oh, you can't see it. Here we go. I want you guys to do that for tomorrow. So G period, this is due Tuesday. Okay?
And we need to know